Thomas, you can start sharing your screen and we can move on to the next talk of today. So we have seen both last two speakers talking about a lot about cell design and optimizing the reactions. I think now Thomas will also talk about how to optimize the measurement of the experiment and how Metrohm Autolab is working on it. So Thomas, feel free to start, and then I'm looking forward to your presentation.
Yeah, thank you, Heike, for the introduction and also for this day that has been very interesting and inspiring so far. So I am a product manager at Metrohm Autolab, and I'm going to talk about potential stat and the instrumentations and new developments that we've been working on, and especially through a new instrument that is called VIONIC, and that's going to be the core of my presentation. And I'm going to be focusing on two new features and new developments that I will put into the context of electrocatalysis. So first, a bit of an outline. So I will first give a short introduction of Metrohm Autolab, the company. Then an overview of this new instrument I'm talking about, VIONIC, powered by INTELLO, that you can see here on the left. I'm going to take the pointer right now. And then I'm going to talk about two features that are unique and specific to this instrument, the second sense electrode and the seamless measurement. So of course, it will be a bit more clear in a couple of minutes when I will give more details about it. So first of all, Metrohm Autolab. So we're part of a bigger group that is the Metrohm Group that is specialized in analytical chemistry, providing tools and instruments and solutions in a wide variety of analytical chemistry. And more specifically, Metrohm Autolab. So we're specialized into instruments for electrochemistry with a very wide range of instruments that you can see and that some of you might be familiar with. We have a modular instrument where you can do different types of techniques depending on your research, multi-channel instruments, more compact instruments, and the new instrument that we have that is VIONIC here on the top. We also provide accessories and supplies such as cells, electrodes, automation solution, software solutions. So we have Nova for our portfolio, and we introduced a new software for our new instrument that is INTELLO. And we also provide service and support for our instruments. So the new instrument I'm talking about, VIONIC, powered by INTELLO. So it's a bit of a special instrument, and we launched it earlier this year. So this instrument combines a lot of specifications and features in one single instrument, and it's aimed at covering research and development from very fundamental level towards more applied research. And the span of the specifications is, for example, that you can choose the compliance of your instrument, and you can switch from a very high accuracy measurement for fundamental research or to higher compliance voltage for more applied research. This instrument also comes, and I think it will ring a bell to people working in electrocatalysis, and especially with platinum, for example, is provided with an analog scan generator, which comes as standard, and there is no add-on required. So you can choose this technique if you want to perform cyclic voltammetry in a linear way. It also comes with impedance spectroscopy up to 10 megahertz. We also have a sampling interval that can be as low as 1 microsecond. We cover current ranges from below the nanoampere up to 6 ampere. And it also comes with the possibility of operating untethered, which means that it can keep doing your experiment, and you can remove your laptop and work on something else at the same time. And it also has some features that are important when you're doing research and development, which is automatic data saving and inboard memory that allows you to safely keep your data in the instrument until they are fetched by your laptop. And this new instrument also comes with two new features, which are the seamless measurements, and I will focus on that later, and the second sense electrode that I will detail as well. So the first topic I want to address is the second sense electrode, and I will show how it can be used for electrocatalysis research, especially to measure the counter-electrode potential and what kind of application this is targeting. So this second sense electrode is a new electrode that allows you to collect an additional potential in your cell versus your reference electrode. So usually when you perform electrochemical measurements, you have a 3 electrode configuration, your working electrode where your reaction of interest is occurring, you have your counter electrode where the current is flowing, and you have your reference electrode. With this second sense, you can measure an extra potential, which is something more than just the potential of the working electrode. What does it mean? Mainly, it means that you can record the potential of your counter electrode. So if you connect this new connector to your counter electrode, the current will flow at the counter electrode. You can apply a potential at the working electrode, and at the same time you can monitor the potential of the counter electrode. So here on the screen you have an example of a very simple CV, and in blue it's the waveform that is applied at the working electrode, and you're measuring a certain type of current that will give you the CV on the bottom left here. And at the same time, you can see what's happening at your counter electrode by measuring the potential, and you see that it follows what's happening in the current in this case. The question might be why do you want to monitor the potential at your counter electrode? I'm going to use examples to illustrate that. The idea is that counter electrodes in electrochemistry usually are neglected, and one assumes that if the counter electrode is large enough, whatever happened there will be minimal and can be neglected, and any reaction occurring there will never interfere with what is happening at your working electrode, because your working electrode is the material or the catalyst that you're interested in. And actually, if you're using a type of material such as platinum, which is very common for counter electrode, what is happening at the counter electrode is not always negligible, and especially platinum can dissolve under anodic conditions. So if you're studying cathodic reactions, so if your working electrode is, for example, CO2 reduction or hydrogen evolution, the potential of your working electrode will be negative. Thus, the potential of your counter electrode has to be positive. And if the potential of your counter electrode goes above a certain threshold, then you can start initiating the dissolution of platinum. And the platinum that you're dissolving from your counter electrode can go and contaminate your working electrode. So it can be very interesting to know the potential of your counter electrode to make sure that you're never going beyond that threshold. An example of that is the case of the hydrogen evolution reaction at non-noble materials. We know that platinum is a very good catalyst for hydrogen evolution. And if you're studying another catalyst and that you're using a platinum counter-electrode at the same time, it might dissolve and the platinum might reach your working electrode and start changing the activity. So you can see here, for example, on the bottom, if you use just graphite working electrode, the over potential for the hydrogen evolution is very low, and you don't have a lot of current. And if you use a graphite counter electrode, the graphite will be completely inert. But if you use a platinum as a counter electrode and you keep performing this linear sweep voltammetry here, you will see that the more you do it, the more the activity of your graphite electrode will increase, which is a bit unexpected from such an inert material. It's not a good catalyst. And actually, what's happening in this case is that the platinum from the counter electrode is depositing at the working electrode. And this can be monitored by, as you can see on the right here, following the potential of the counter electrode while you're cycling. And if the potential goes beyond this threshold, then you know that your platinum is dissolving and might be contaminating your working electrode. So this can be interesting to know, and it's possible by monitoring the potential of the counter electrode with a second sense electrode in your cell. And as I was saying, it's relevant for a study of cathodic reaction, and we heard already today about hydrogen evolution, CO2 reduction reaction. So if you have, for some reason, to use a platinum counter electrode, it's important to know what's happening there. And of course, it's a bit less known, but if you're studying anodic reaction, platinum can also undergo what is called cathodic corrosion. I'm not going to go into the details, and you have some literature about that, but in certain conditions, if you have, for example, a large concentration of cations in your solution, the platinum can also corrode under cathodic condition. And again, whatever you produce at this platinum will go and deposit to your working electrode, and again contaminate and change the response of your electrocatalyst. So the monitoring the potential of your platinum counter electrode can also be important if you're studying anodic reactions such as the oxygen evolution reaction, methanol oxidation, and so on. So there is more about that, which is like you can measure the potential, but you can know a bit more. And maybe you're familiar with electrochemical impedance spectroscopy, but it's a technique that allows you to obtain some information such as the electron transfer rates of a reaction, adsorption processes, the structure of your material or your catalyst, diffusion occurring in your cell. And usually it's applied to the working electrode because this is where you want to get information. But with the second sense electrode, you can also monitor what's happening at your counter electrode. And so if you have some adsorption process that might interfere with your the environment of your cell, it's also very important to know what's happening at the counter electrode too. So with this second sense, you have a view not only about one half of your cell, which is usually what you get with a normal 3-electrode configuration, but you have a view on the complete cell, including the counter electrode. So I've been thinking about like quite fundamental research when you're working in a 3-electrode cell without separation between the counter electrode and the working electrode. But you can think also of like more application-oriented research when you start to do, for example, bulk electrolysis. I'm thinking of like CO2 reduction reaction when you want to produce a lot of product to measure Faradic efficiencies or these kind of things. You will use a cell with a separator between the counter electrode and the working electrode. And you will use a membrane or a freight to separate them. And this is a part of your experiment that you cannot control. It's just separating the compartments. And with the EIS, for example, you can measure the resistance induced by this membrane between the two compartments. And it can be important because this resistance can increase if, for example, you have some product that come and clog or degrade the membrane. Your cell might be changing over time, so it can be interesting to monitor what's happening in the counter electrode compartment during your electrolysis. So again, I think the take-home message of that is that with this second sense electrode, you've got a bigger picture of your cell, and you know what's happening on both sides. The working electrode, which is definitely interesting, but also the counter electrode, which might be interfering without you noticing. So this is one aspect, and you can see that it goes towards like very fundamental research, maybe, and more applied research when you do electrolysis. The second aspect of the second feature of VIONIC that I would like to talk about today is the seamless measurements. So it's a new concept, and it's totally unique to VIONIC, powered by INTELLO, the software. And the idea is that modern potentiostat offer very high flexibility to program complex sequences of or unique waveforms, or you can be very creative in the way you want to explore your system. We go to very high precision and accuracy in the sampling. We are reaching very high sampling rates. I was mentioning 1 microsecond in the beginning. But the question is, how close does the instrumentation come to really meeting these expectations? How are we following that with the instruments? This can be answered if we think of a way an electrochemical measurement is done. An electrochemical measurement, you apply a signal and you measure a signal. So, for example, if you're in a potentiostat, you apply a potential and you measure a current. And if you want to explore a system in a certain way, you will probably, for example, apply a potential and then a potential ramp and change the scan rate and these kind of things. And seamless measurements are measurements where all the commands will be executed seamlessly one after another, and the different signals will be measured seamlessly one after another without any gap or delay in the applied signal or the measured signal. So I'm taking this example of the horse in motion that is quite popular and quite old, but the idea that I want to, this is the system I want to study this horse in motion, and I'm going to send to the horseman a signal every, let's say, 200 milliseconds, just make sure that the horse is moving, and I will just repeat this signal every time I want to take a picture. And so this is what is expected to happen. And if I take a picture every 200 milliseconds, I will get this little movie here on the bottom left. But it's actually not always what's happening because of the very specific thing that we're talking about, which is a potentiostat. So I'm not going to go into the details of how it works, but basically a potentiostat controls a potential between the working and the reference electrode. It can generate a potential waveform, so it can be just a straight potential or a potential sweep or a sine, whatever, and you measure a signal. So, for example, the current between the working electrode and the counter. So if you want to know more about like how it works, we have an application note about that, and I think it's quite informative to know how the instrument is working, because it also influences the kind of measurement that you're doing. But it is possible that sorry, I think I'm missing a slide. Yeah. Okay. Yeah. So I'm gonna add something here. So the thing is that nowadays, like potentiostat, and I'm saying nowadays, but it's for more than 30 years, potentiostat are controlled by computers. And so there is like some communication happening, and when you're sending a signal to execute a command or to record a signal, there is some delay happening. So the first thing that can happen is that there is a delay in the applied signal. And for example, I'm sending a signal every 200 milliseconds saying to the horseman, just make sure that the horse is moving. And at some point, I want to tell the horseman, oh, just make sure that the horse is moving faster. But at the moment this happened, like the time it takes for me, for example, to say this sentence will just like confuse the horseman. And what will happen is that basically it would be frozen and the observation will be distorted. In terms of electrochemistry, what happened is that I'm sending, I'm going to take an example where I'm sending a waveform and I'm changing the speed here in blue at which the potential is applied. And I'm recording the current. And so this is in green, the current response of my system. And so if I send a first signal and then a second one, very immediately the electrochemical system will reply. But if there is sort of a hiccup between the first signal that I'm sending and the second one, and in this case, it's, for example, 20 millisecond gap where I'm like, oh, wait, I want you to send this second waveform, then the system will be just holding, and it's a real system. It's a dynamic system, so it cannot just hold And so there will be something happening in between that you will not be able to capture, and that will be just due to the fact that there is some delay in the way you're applying the signal. So the behavior of the system can change if there is a delay between two comments. And so how can we explain that, and how can we fix that? So the idea that, like, as I said, we have like computer controlled potential stats, and when you want to execute a series of commands, most of the potential stats use a sequential communication between the signal generation and acquisition. You have a sequential command execution as well, and so it means that it's not really seamless. So the computer sends a signal to what is called the embedded processor, which is the inner brain of the potential stat, which send the message to a signal generator, which takes a bit more time, and then you have the signal acquisition that sends some signal back to the embedded processor. So every time you want to go from one command to another, you have some almost unavoidable delay due to these different steps. And what we did with VIONIC is that we worked on the embedded processor, which is the brain of the potential stat, and we made it smarter in a way so that the embedded processor can pre-plan the series of commands and can execute the different commands without communication with the rest. And so it makes that the communication and the execution of commands can be completely smooth and seamless, and there is no more gap in the way commands are applied one after another. And the second thing that can happening is that not only you are not sending the information exactly as you wanted, because there is like this communication delay, but also in the way you measure the signal. So you can also observe the same system again, and then you switch something in the parameter that you're using to study the system, and this will induce some gap where the instrument is not able to measure what's happening because it's busy with something else, such as sending a message like, oh, change this parameter right now. And so instead of observing what you're supposed to observe, you will have some incomplete observation of your system. You will be missing something at the moment when the instrument is busy doing something else and cannot be measuring. And if you think of electrochemical information, for example, it means that you will be missing some data points, and depending on the system, it can also lead to wrong interpretation. So here we took the very simple example of step potential applied to a system. If the electron transfer is diffusion controlled, you will have this kind of exponential decay in black here. If you have a kinetic control, you will have a straight jump from one current to another at the potential jump. And if you have a mixed control, you will have something in between. And so if the system you're studying has a diffusion control, controlled electron transfer in black, and that your measurement is not seamless, then you will inevitably be losing the beginning of the exponential decay here. And so if you lose a bit, then you might think that, okay, my electron transfer is a mixed control. Or if the gap is even bigger, you may think that it's a kinetic control event. With a seamless measurement, you have the full picture from the very first data point that you can measure to the last. So it gives you again like a better picture of what's happening at transition between different commands. And if you're studying fast systems, then it can be extremely important to have the full picture. And the technology behind that, I'm not going to go into the detail, but how it was made possible was to change the way the potential and the current are sampled in the instrument. In conventional potential stat before VIONIC, the potential and the current were sampled one after another because it's not possible to sample two signals exactly at the same time, and there is some delay between the two measurements, and so it just induces this tiny gap that I was talking about before. And so the result of that is that you have some resolution loss and delays inherent to the system, the instrument that you're using. But with VIONIC, what we managed to do is to find a way to sample exactly at the same time the potential and the current. And these are like two parallel paths to measure two signals. And so there is absolutely no more delay between the measured potential and measured current, or applied potential and measured current. And so it has the first benefit that you can have seamless measurements, so you don't lose any information. And it also increases the resolution of your instrument. Well, that's the two features I wanted to talk about today. So the second sim that allows you to measure the potential at the counter-electrode, for example, and I think it's relevant for fundamental research and scaled-up applications, such as the bulk electrolysis, and seamless that is more oriented toward fundamental research and when you're studying fast events, or sensitive measurements when you want to be sure that you apply exactly the right waveform to your system. So thank you for your attention, and if you have questions, raise your hand. If you have any suggestions as well, please speak up. And if you have any ideas on how these features could benefit your project, I'd be very interested to hear about it. Thank you.
Thanks, Thomas, for this very interesting talk. Indeed, if there are any questions specific to this talk, please raise your hand. In the meantime, a short question from my side. So, Thomas, we've seen massive acceleration in the testing capacity towards batteries, lithium-ion batteries. What can we learn in standardization or in high throughput research from that market that we could also apply on the fields of electrocatalysis design?
Well, I think that we're talking about like two things. If we think of that, we think of being like having maybe instrument that may be more focused towards one application and that do exactly what they are made to do. And the second thing is maybe like I think when you're talking about like battery research, so sequential or parallel measurements, that's what you're thinking of, right?
Yeah.
Yeah, it's that's something that yeah is happening, and for the electrocatalysis, I think we should learn as well, and I think the instruments are ready because they're already ready for the battery research, and so we already know how to do this kind of sequential or parallel measurements on high number of samples. So yeah, maybe there is like some bridge to build indeed in between, but I would say that the instruments are ready and might be like as I was talking about today. So this instrument I was talking about is dedicated to cover research from very fundamental to a bit more scaled up and application oriented research. Yeah, if we're talking about more application oriented research, we might focus a bit more the specifications toward a higher end.
And I know that from your side, you are trying to make the most flexible but also most powerful tool for researchers to use in their research. How much are you also thinking about or working on more standardization? So making sure that one of your customers is doing exactly the same script than another customer. Is that something that you are working on? Is that something that you are involved in regarding the ISO standards or other type of standards?
Yes, we are. Like our instruments are like we are following ISO. We have an ISO standard for the company, and all the instruments are tested, and we provide some specifications, and they are given within a certain margin, and this is available to the public. So when you buy an instrument, you know that if you're doing impedance up to a certain frequency, your results are reliable within like 0.1%. If you're so we have like very specific specifications, and each technique has also can be looked into. Each like we have different technique. I'm thinking of the analog scan and the staircase voltammetry, for example, which are two different things, and all these things are tested, and when the instruments come out of our production line, they are tested and they follow standards. Yeah.
Great. Any other questions from the audience? I'll give you a few seconds to think about it. Otherwise, Thomas, I want to thank you for this elaborate talk on your efforts to accelerate and to make it even easier for research.